Okay, hello. Welcome, Precalc C. On Thursday and Friday, you had a homework assignment with 6 rational functions that you had to graph. They're all pretty hard, although hopefully by doing many of them, you are starting to get better. But you never know what's going to happen next, which makes them kind of, each one kind of special and exciting, but also makes it kind of difficult. So I thought I would go over some of them now. So, yeah, let's go. Number 19, x cubed plus 2x squared minus 5x over x squared plus 4. I've done all these problems before, but I'm just going to put the paper down and just use my wits. So how do I do this? Well, let's begin. I can certainly factor an x out of the top here, giving me x squared plus 2x minus 5, and that does not factor, so that makes me kind of sad. I think I have seen this before. Well, I can't remember, so let's just do it. Let's do the quadratic formula. It is going to have roots, of course, so okay, anyway, here we go. Negative b, so negative 2 plus or minus the square root of b squared, so 4 minus 4 ac. So yeah, this same numerator, I believe, was recycled from a problem that we did already together, which was problem, well, I don't know, problem 20. Yeah, so it is the same numerator from problem 20, so, okay, great. Might have almost been faster to complete the square here, but never mind. Yeah, so this becomes negative 2 plus or minus, that's root 24, which I know to be 2 root 6. And so what I get here is negative 1 plus or minus root 6. And we discussed in class how negative 1 minus root 6 and negative 1 plus root 6 can be approximated, given the fact that root 6 is somewhere between 2 and 3, so calling it 2.5 for whatever, this is about negative 3.5, and this is about negative 1.5. Okay, and well, that enables me to write this polynomial in factored form, which is it's x times x minus negative 1 minus root 6 and x minus negative 1 plus root 6. And on the bottom, I suppose we should discuss that x squared plus 4 is always positive. So that is very interesting. Since this is always positive, and I think this is the first time this has happened so far in this class that we've graphed a rational function where there were no roots in the polynomial in the denominator, well, that just means that it's always positive. So there are going to be no x values which make that denominator 0. And so one thing we might note is that the domain of this function is in fact all real numbers, because it's just a polynomial on the top and a polynomial on the bottom, which is never 0. So therefore, we will have no vertical asymptotes. And I guess also you must appreciate that when it comes to making the sign chart for this rational function, you have to just look at that thing on the bottom and just say, it's always positive. If x squared plus 4 is always positive, then it's just always positive. Therefore, the sign of this rational function will be completely determined by the sign of the numerator. And so I am essentially now going to make I'm going to make the number line for the rational function, saying when it's positive and negative, but that's just the same as analyzing the sign of the cubic in the numerator. Okay, and what do we know? There's a sign change at 0 because it's a single root at 0. There's a sign change at negative 1 minus root 6, and there's a sign change at negative 1 plus root 6. And that's a cubic in the numerator, so the end behavior is going to be what it is, which is it's going to start negative, then positive, negative, positive. Okay, so feeling pretty good. I got I'll just say some other things here. I have my roots. What are they? There's 0 and negative 1 plus or minus root 6. So that's good to know. I have my domain, which is all real numbers. There are no vertical asymptotes. I know when it's 0. I know what the sign is. The y-intercept is quite boring because, you know, because 0 is a root, the y-intercept is just 0, 0. So didn't really learn anything new there. The last thing to do is polynomial long division. So let's do that now. Let me kind of be very careful about it so I don't make any mistakes, because that would be sad. So, doing the polynomial long division, x squared goes into x cubed, x times x cubed plus 4x, and then subtract 2x squared. Yeah. And then there's kind of like a plus 0 here type situation. So that's going to go in plus 2 times, and so we get 2x squared plus 8. And when we subtract, get negative 9x minus 8. Okay, so I am now pretty sure that that is right. I mean, you know, well, yeah, I bet it's just right. Minus, okay, yep. Okay, so what have I just learned? I've just learned that this function is really just x plus 2, but with a remainder of negative x minus 8 over x squared plus 4. And yeah, I mean, I could even just check this if I wanted to be like extremely careful or something. I get x cubed, I get multiplying back through, I get 2x, let's see, is this the best way to do it? I get an x cubed, I get a 2x squared, so yep, and then I get a 4x minus, sorry, I get, well, I guess this is just right. I don't feel like checking this, I decided. 4x minus, yeah, 4x minus 9x is 5x, and then 2x squared, yup, and then a minus 8. Okay, so we're good. The last thing I might want to do is write this as x plus 2. Just to kind of clarify what's going on here, I'll sort of like factor a 9 out and a negative out of that numerator, leaving me with x plus 8/9 all over x squared plus 4. Okay, and now that's just a little bit more convenient. So this is my format to now look very carefully at this function and conclude something. Well, what do I conclude? I conclude that when x is very large, say, you know, 1,000, then this quadratic in the denominator is basically 1,000,000, and this numerator is basically like 9,000, which is just almost nothing compared to 1,000,000. So, because this quadratic is so much bigger than this linear function, then what I can say is that for very large values of x, this whole remainder term is almost nothing, and this function is therefore going to look a lot like y equals x plus 2. And so, we have a slant asymptote at y equals x plus 2. And when, if ever, do I cross it? Well, the only time my function is ever going to equal x plus 2 exactly is when that numerator is when this entire remainder term is 0. And the only way that will be 0 is when the numerator is 0, which will only happen when x is negative 8/9. So f crosses y equals x plus 2 at x equals negative 8/9. And by the way, when x is negative 8/9, what is 2 more than negative 8/9? Well, I just add 2, which is 18/9, and so I get 10/9. And so that is the point at which this function is going to cross that line y equals x plus 2. Okay, now it's just a matter of graphing it. So we go. I don't know what's a good scale. So just kind of improvise. So 1, 2, 3, 1, 2, 3, 4. Something like that. 1, 2, 3, 1, 2, 3. Alright, what do I know? I have no vertical asymptotes. I have no horizontal asymptotes. I have a slant asymptote of y equals x plus 2. And sort of there it is. Let me add some roots. Where are the roots? There's 1 at 0. There's 1 at -1 plus root 6, which is about 1.5 we say. And there's 1 down here at -3.5. And now we begin to graph. What do I know? I know that my function... Oh, one more thing. There's only one point at which this function crosses the line y equals x plus 2. And that is at -8/9. So if I go over here to -8/9, comma 10/9, boom, 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 I have a cross. But there are no other crosses. Therefore, my function is going to... Okay, I did need maybe a little bit more space, so I'll just kind of cheat and draw kind of off the board. But basically, this function is going to look a lot like the line y equals x plus 2. It's going to sort of hug this line for some period of time, and then a cross, so imagine it, looking more and more like that line as we go down. But it's negative until -1 minus root 6, at which point it becomes positive, and it's positive until 0. So this does require some sort of confidence in what you're doing because, well, I just know I go through this point, and I know that there's a root here at the origin. I definitely don't know what that relative max is, because we need calculus for that. And yet, this is pretty much right. What else? I will be negative in between those two roots, so something like that. And then possibly, that's not so accurate. Possibly it's more, like that, but whatever. I don't really know or care. And then positive thereafter, looking more and more like the line y equals x plus 2. So I think this is just pretty much right. I know I don't cross this asymptote ever over here, so I will stay below it. And from memory, I think this is completely correct. You can graph it on Desmos to check yourself, but hopefully that logic was all clear. Okay, good. 1 down, 3 more to go. 26 and 27 are actually functions which I sometimes do in class. So I have a completely worked out, written solution to those two. So I'm not going to go over those two because I'll just give you my PDF of my work that's already been done, which some people might prefer, but some people want to hear all the explanations. So for 2 of them, you can just see exactly what I did and check your answers immediately. And for these other 4, you can watch this video or not. You can sort of skip through it, I suppose, and hear my explanations for sort of why I did what I did and how I knew that and all that kind of stuff. So it's potentially more valuable, but it's more time consuming on your part. So that'll be a mix. That way I only have to do 4 of these. Okay, well, here we go. This is number 25. Just double check. Yeah, let's do it. Well, first of all, I noticed something really nice about that cubic up there, which is that the first 2 terms have an x squared in common and leaving me with x minus 3. So this is a factor by grouping situation. So x cubed, I'll kind of do this off to the side, minus x plus 3 can be written as x squared, x minus 3 minus x minus 3. And therefore, by factoring out the x minus 3 and being left with x squared minus 1, I know that this factors as x minus 3, x minus 1, x plus 1. Okay, so that was like some side work. You could kind of almost do that in your head. But, right, what have I learned? Well, I've learned that this rational function has roots x minus 3, x minus 1, x plus 1, and the bottom, of course, factors as x minus 2, x plus 2. Alright, so nice, happy, chill, simple, small integer zeros in the both polynomials in the numerator and denominator. So then I will just make my number line with all these things in there. So -3, -2, -1, 1, and 2. And by considering the corresponding polynomial, which is a 5th degree polynomial, which is the product of all of these together, it will be positive and negative in the exact same times that this function is positive and negative. And it will be a quintic with these 5 single roots, changing sign in each one of them, positive leading coefficient, so end behavior like this. And that's how I know, basically instantly, that this is going to look like negative, positive, negative, positive, negative, positive. Okay, wow, what now? What are my roots? I'll just list them kind of right here to save space. They are 1, negative 1, and 3. So that's nice. What else? I'm going to have some vertical asymptotes. What are they? Well, x equals 2 and x equals negative 2. That's a fact because near those numbers my denominator will be very tiny, making the function very huge. What else? I guess I can find the y-intercept. If you plug in 0, you can see immediately that that is negative 3/4. So that's some extra point for free. What am I forgetting? Maybe nothing. Roots, vertical asymptotes, sign chart. Maybe you were good to go. Let's do polynomial long division because we can, so we should. So this is x cubed minus 3x squared minus x plus 3. And I will divide by x squared minus 4. Alright, let's do it. It goes in x times x cubed minus 4x. And let's see, that will be negative 3x squared, negative 1 minus negative 4, so that's negative 1 plus 4, so that's minus 3x plus 3. And that will go in minus 3 times, so that gives me negative 3x squared minus 12, no, plus 12, chop. And, well, what does this give me? This gives me negative 3x minus 9. Yeah, so I think I remember this problem because, well, okay, let's see what we got here. We have, therefore, that this function looks like x minus 3, and then I'll just factor out sort of minus 3x plus 3 all over x squared minus 4. Okay, so having done the polynomial long division and having written out the function in this new format, I see that, yeah, the remainder is negative 3x minus 9, but factoring it nicely tells me that my function crosses the line y equals x minus 3 at negative 3. Okay, so what do we have? We have a slant asymptote. Y equals x minus 3, which f crosses at the point x equals negative 3. And let's see, have I done that right? I'm sort of doubting myself a little bit. I guess it's good. I guess I could have checked these all in advance. Because, let's see, when x is negative 3, so I get negative 3, negative 6. Okay, well, that's probably right. Well, how can I... probably should have done this in advance, but too late. I will take a mere second right now. I am pretty sure I'm right, but when I make a mistake, it kind of does ruin the whole video. So, super professional operation here that we have going on. Yikes! Professional operation we have going on, but yeah, I'm just good, I think. Okay, it's being super annoying, not doing anything in the normal way you would want. Whatever, I'm sure I'm right. Okay, good. Well, yeah, we graph. Let's go. Boom, 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 boom. Boom, 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 boom. And what do we know? Well, let's see. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. If there's some kind of mistake, I guess I'll just find it. We have a vertical asymptote at x equals 2, negative 2. We have a vertical asymptote at x equals 2. We have a slant asymptote y equals x minus 3. So that's kind of that one, like there. And then, interesting. Okay, sure. I don't know why I'm being sort of paranoid or something that this is wrong. Ah, it is wrong. -1 minus -4 is -1 plus 4. It's plus 3. I apologize if you've been screaming in silence this whole time, because that does make this 3x. I knew something. I knew it. Ah, crazy. So that means that unlike what I wrote there, if you do polynomial long division wrong, then everything's wrong. -1 minus -4 is -1 plus 4. That's positive 3, of course. Okay. Well, I wasted a couple minutes of your life, but at least I fixed this problem now, because I did sort of have a memory that that was wrong. Because now, okay, that's positive 3, but that's still -9, so now factoring out a 3 leaves me with x minus 3, which means it's still a slant asymptote of y equals x minus 3, but the only time that it crosses is when that numerator is 0. Well, that numerator will be 0 only when x is 3. But of course, when x is 3, we get 0. So I actually didn't learn any new crossings there. Because after all, what are the roots of my polynomial? They are 1, -1, and 3. 1, 2, 3. So in other words, right here. So okay, because I had here's what I'm trying to say. Because I already knew that 3 was a root of my polynomial, and I knew that once I determined that the slant asymptote is y equals x minus 3, then I for sure cross y equals x minus 3 once at 3. So what I learned by this polynomial long division, besides the fact that I learned that my slant asymptote is y equals x minus 3, I also learned that the only time that my function is equal to x minus 3, in other words, the only time I cross the slant asymptote, is when this remainder term is 0, which happens only when the numerator is 0, which happens only at x equals 3. And so this root, 3 comma 0, where my function crosses the slant asymptote, is the only time when I cross the slant asymptote. Alright, and now I can just finish this problem. 0 comma -3/4 is my other point that I know about. That's the y-intercept. Now I just play the connect the dots. I'm going to start very close to this asymptote. And what do I know? I know I stay negative all the way until -3. Oh my god. Is this sign chart just totally wrong too? Oh my god. Sort of off today. I apologize. Let's make that sign chart again because it was just totally wrong. Whew. Okay. -2. -1. 1, 2, 3. This is why class is better than videos sometimes, because someone would have screamed 15 minutes ago about that mistake. But, okay, here we go. It's a quintic, so negative, positive, negative, positive, negative, positive. Let's just put a positive spin on this by saying I am modeling the learning process, as they say. Notice how I caught all my mistakes, because when I went to go look at my sign chart, I noticed that it made no sense. There is a sign change at -2, and what happens at -2? Well, near -2 my function is infinitely big. My sign chart tells me that to the left of -2 my function will be negative infinitely big. Which means I already kind of knew, this, sort of. Well, if I also know that my function is always negative until I get to -2, and also that when my function is a very large negative, it will look very much like the line y equals x minus 3, and if I also know that the function doesn't cross the line y equals x minus 3 down here, because it only crosses the line y equals x minus 3 here, then it means that I must hug close to that asymptote while never crossing it, and then eventually just end up down there. So its function is going to look something like that on the interval from negative infinity to negative 2. And notice I'm just kind of winging it a little bit, right? This might not be so close, it might be kind of much farther down, but that is the general sort of shape and location of the function. Okay, the rest should be easy because when I'm a tiny bit more than negative 2, I will still be huge, but now huge positive because my sign chart says so. So that means I'm going to be way up here, positive until negative 1, at which point there's a root. Negative in between negative 1 and 1, so boom, 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 boom. And well, going through that y-intercept, then in between 1 and 2, my function will be positive. And when I get to 2, it's going to become huge, positive huge to the left of 2. But for numbers a little bit more than 2, it will be negative huge. And, well, still negative until we get to 3, at which point there's a root, positive thereafter. So I sort of cross, and then at some point this will start going back up like that, and will hug the asymptote y equals x minus 3 forever. Woo! Good. That is right now, so that makes me happy. Could have been slightly more efficient, but okay. Great. 2 down, 2 to go. Yeah, 2 down, 2 to go. And just kind of lock in, no mistakes. What are the next two? They are 31 and 37. Let's go. 31. Well, here we have a function, 31, x cubed minus 2x squared minus 11x plus 12 all over x squared minus 4x plus 4. Okay, this is a great problem. I remember this one also. Well, for starters, I need to find roots. So let's see. Should we do this the lazy way or the awesome way? The awesome way would be to take this polynomial really seriously, this x cubed minus 2x squared minus 11x plus 12, and to say something like, well, okay, let's apply Descartes' rule of signs to it and see that it starts positive. Then there's one sign change and there's another sign change, so it has either 1 or 2 positive real roots. If I plug negative x in here, that will be now negative, negative, positive, positive, so therefore there's exactly 1 negative real root. So maybe this is worth it. I don't really want to do all this every time because I'd like to just sort of get on with myself. But there are 2 sign changes, that's a fact, and there is definitely 1 sign change in the numerator polynomial flipped over the y-axis. So that's a situation. It doesn't super help me very much, to be honest. I can also apply the rational root theorem to this, and I can see that since my constant term is 12, then basically this is going to be like a 1, 2, 3, 4, 6, 12 situation. So that gives me still 12 numbers that I need to search for. Oh, let's just go with our trusty law of ones. Surely that won't fail us. Let's see, I don't actually know what happens. I get a 1, 1, negative 1, negative 1, negative 12, negative 12. Boom! That's so wonderful. So 1 is root, and it just is. Yep, if you plug in 1, you get 1 minus 2 is negative 1, minus 11 is negative 12, and 12 is 0, so that's great. Also, these are the coefficients of the quotient polynomial, which is x squared minus x minus 12, which itself factors as x minus 4x plus 3. Double checking that because I don't want any mistakes. Yeah. Alright, so after much work, here's what I have learned. This function is in fact x minus 1, x minus 4, and x plus 3 in the numerator. And in the denominator, Well, that's a perfect square trinomial. That's in fact just x minus 2 squared. Alright, so this is kind of an exciting new thing. I mean, maybe exciting is an exaggeration. All of this, I'll put a box around all this because this was all just me analyzing that cubic in the numerator. But here we have it now in factored form. Well, what's new, and so I say exciting here, is that we have a vertical asymptote at 2. So maybe I'll write that down. So vertical asymptote at x equals 2. We also have some roots. What are they? They are at 1, negative 4, 1, 4, and negative 3. Interestingly, this vertical asymptote, okay, it's clearly a vertical asymptote because if you give me a number which is very, very close to 2, and you plug it in here, then that's something very, very tiny, so that if the denominator is tiny, then the fraction is huge. The thing that's different about it is that the denominator has kind of like a double root. So what's the significance of that? What's the significance of the double root in the denominator? Well, I'll say some things about this maybe in a minute, but for now, when we go to make the sign chart, personally, my preference is to just avoid this entirely and to just say that, explain this in one of the videos from last week, that since x minus 2 squared is always positive, I look at this fraction and I just look at that denominator, and to me that's just saying always positive, except when x is 2, of course. So since it's always positive, and if I want to know the overall sign of this rational function, then that's just going to be whatever the sign of the numerator is, because the denominator polynomial quadratic isn't changing the sign of the function in any way. Okay, so one option is to simply just put those roots of the numerator onto your sign chart. This is kind of the minimalist way, and I guess I'll do it both ways. This is a cubic, so it's going to go negative, positive, because leading coefficient is 1. This is how I like to do it. Other people don't like this. They like to somehow include 2 in the story. Maybe to remind themselves that something dramatic happens at 2. But, well, if you want to do that, fine. But you better be careful that there is no sign change at 2. Because since 2 is a double root, if you think of the corresponding polynomial, which is a 5th degree polynomial, there'll be a single root at 1, a single root at 4, a single root at negative 3, but a double root at 2. And when a polynomial has a double root, then the function just does not cross the x-axis, so there's no sign change there. So if you insist on including 2, which is fine, students seem to prefer this, then you just have to know that this is a quintic, that you should be thinking quintic now, and the end behavior for the quintic will be like this, because the leading coefficient is positive, and it will be negative, positive, negative, but now no sign change at 2, because it's a double root. And then a sign change at 4. So, okay, so hopefully everyone sees that these 2 sign charts are substantially the same thing, and so either one is perfectly fine, whichever one you prefer. Okay. La 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 la! What else do we need to do? We can find the y-intercept. What is it? Plug in 0, and you just indeed do get 3, so that's nice to know. Let's do polynomial long division. So we can check the end behavior. So x cubed minus 2x squared minus 11x plus 12 divided by x squared minus 4x plus 4. Let me make sure that I don't make any mistakes. It's going to go in x squared is going to go into x cubed x times, and this gives me x cubed minus 4x squared plus 4x subtracting gives me 2x squared negative 2 minus negative 4. That's plus 4, so that's 2, and then that's minus 15x. It just is, and then plus 12. So that is going to now go in 2 times. So we get 2x squared minus 8x and then plus 8. So subtracting here gives me negative 15 minus negative 8, so that's plus 8. So that's minus 7x plus 4. Okay, those numbers sound familiar to me. So I'm ready to declare that this function really is the function x plus 2. And then let me pull out a negative 7 and write that as 7x minus 4/7. I think I did that right. Yeah. All over x minus 2 squared. Okay, so yeah, the only time that negative 7x plus 4 will be 0 is when x is negative 4/7. That's just right. So, writing it like this tells me two things. It tells me that I have a slant asymptote of y equals x plus 2, and it also tells me that my function will cross that slant asymptote one time and one time only at x equals 4/7. And by the way, when x is 4/7, what is the y value on the line y equals x plus 2? Well, I just add 2 to 4/7, so that's 4/7 and 14/7, so that's 18/7, which is like 2 and a little bit. Okay, without further ado, we graph this. Okay. Trying to pick a scale on the fly. 3, 4, 1, 2, 3, 4. Yeah, let's go. What do I know? There is a vertical asymptote at x equals 2, and there is a slant asymptote of y equals x plus 2. So we got something like that. Cha-cha-cha. Okay, maybe. Right, what else? I have some roots. What are the roots? There's one at 1, there's one at 4, and there's one at negative 3. What else do I know? I know that there's a y-intercept at 3, and I know that this function crosses the line y equals x plus 2 one time only, and that's right here at 4/7, 18/7. I'm going to put a dot there too. Okay, and now I'm ready to graph this, I think. If I don't cross the slant asymptote any other times, then it must be the case that I start out at negative infinity, very, very close to that line y equals x plus 2, not crossing it, staying negative until my root at negative 3. What next? Next, in between negative 3 and 1, my function is positive. So, okay, I really don't know what's going on here without calculus, but something like that. We've seen something kind of like this before. It's really playing connect the dots. I know I'm positive between negative 3 and 1. And, okay, then what happens between 1 and 2? Well, what happens between 1 and 2 is my function's negative. At 2, my function's undefined. Near 2, I have a tiny in the denominator, so my function's like infinitely big. But which kind of infinitely big is it? Looking at either one of these two sign charts tells me that I'll be infinitely big negative, right? It's just true that my function stays negative. But, and this is the first time this has ever happened to us, I don't change sign at this asymptote. That's the extent to which this is a kind of a double root. Yeah. On the other side of 2, I'm still negative. So I'm still sort of negative huge, and I stay negative all the way until 4, and thereafter my function is positive. So, okay, in reality it'll probably take a lot longer for this function to get back up to rejoining that asymptote, but that is the big picture, and this is good, and that's right, and everything. Okay, I think there's a little bit more to say about this. And if you're finding this sort of, this double root in the denominator thing a little bit tricky, let me erase this scratch work where we reasoned about our polynomial, and let's just kind of have a sort of a conversation here about what's going on. Well, I can think of sort of two different, let's go. So let's sort of do again that thing that we did 2 weeks ago, where we say, okay, when x is approximately equal to 2, what can I say about this function? Well, now I'm just plugging 2 into the numerator, and what do I get? 2 minus 1 is 1, 2 minus 4 is negative 2. And here I get 5. So 5 times negative 2 is negative 10. So I say that this function is pretty much negative 10 over x minus 2 squared. This to me is sort of the deepest way of discussing the local behavior near 2. And that is to say that near 2, for values, say, within 1.9 and 2.1 or something like that, this denominator just stays the same. This numerator just stays the same. This numerator, pretty much just negative 10. This is just going to be it's going to do what polynomials do, which is just chill around whatever their value is, which is negative 10. Therefore, I can sort of examine the local behavior of my overall function near x equals 2 by sort of holding the numerator constant, thinking of it as pretty much negative 10, and then seeing what happens to x minus 2 squared. Okay, well, what is this function? This is not the kind of function you see every day, but, okay, writing sort of very small, what does y equals x squared look like? Well, we all know this. It's a parabola. It looks like this. All right, well, if that's the case, then, well, maybe I'll switch colors to blue or something. What does y equals what does y equals 1 over x squared look like? Well, now you need to just reciprocate that parabola. This is sort of easily done, right? Here there's this point kind of 1, 1. Here's this point negative 1, 1. Well, when you take the reciprocal of x squared, then the reciprocal of big things will be sort of small things. The reciprocal of small things will be big things. And of course this function is going to be even. And so you get this shape. And what is this shape? I call it volcano. I think there's no E at the end of volcano. This function 1 over x squared is kind of a volcano. And so if I know that, so let me just make a little bit more space, then what does, maybe switching colors, what does y equals negative 1 over x squared look like? Well, that's just upside down volcano. So, alright, zoom, 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 zoom. And I have this kind of vertical asymptote, and it looks like that. And so, what does negative 10x minus 2 squared look like, finally? Well, that's also maybe not so hard to see, right? It's just going to be a volcano, but moved 2 to the right. So, bump, bump, and with a vertical asymptote at x equals 2, of course, and it's going to look kind of like that, and and stretched out by a factor of 10, okay, whatever. So this is pretty much y equals, I'll just say negative 1 over x minus 2 squared. In other words, it's a volcano upside down moved over 2. And so I should already, if I have this kind of understanding, then I should already expect, as soon as I see this x minus 2 squared on the bottom, I should already expect, oh, that's just kind of like this function is going to be locally volcano. And after I make my sign chart, I see that it's going to be locally negative volcano. And that's exactly what we see here, right? That based on, I didn't have to even do this analysis to see that this function looks like an upside down volcano at x equals 2. So that kind of explains maybe what's going on. Okay, taking forever, getting an education, learning is hard. This is probably the most difficult one right now, this last one. Okay, gotta finish this and move on with my life. Time is it? Oh yeah, 1:10. Okay, the last problem that I'm going to do is 37. So this is pretty hard homework actually for you. Yeah, this one has a potential pitfall. So I won't spend too much time talking about what not to do, but I bet, based on my experience, that people who did this problem, a lot of you did it wrong. And you did it wrong by pursuing a certain strategy which turns out to be not good. Okay, so let's just do it the right way first. Well, man, so much work to do. Step one, I gotta find some roots. So let's see, is 1 a root? 1, 1, -8, -12. Looks like not maybe, right? Well, okay, let's see. 1, so that's 1, so that's 2, so that's 2, so that's -6, that's -6, -18. Oh my gosh! 1 was not a root. Okay, what about -1 is not going to work either. Oh boy. 2? Does 2 work? Well, let's just go 1, 1, -8, -12. Let me make sure I copied the problem down right. 37x cubed plus x squared minus 8x minus 12. Okay, so, well, we persevere. 1, so that's 2, so that's 3, so that's 6, so that's -2, so that's -4, so that's -16. Did I do this all right? Hold on. 1, 1, 2, 2, -6, -4, yeah? Okay, maybe I just should try -1. Perhaps I'm making a horrible mistake here. Or, so that's 1, -1, 0, 0, -8, 8, -4. Wow. I guess these just aren't roots. Let me try -2. 1, 1, -8, -12, 1, -2, -1, 2, -6, and 12 is 0. Okay, so that took a little bit of work. I'm just double checking everything, and I am right. Okay, so -2 is a root. This was kind of a drag, I suppose. Could I have seen this coming? Well, I don't know. Okay, let's keep going. So that's x squared minus x minus 6, which factors into, oh yeah, which factors into x minus 3, x plus 2. So, let me just double check all that. X cubed plus 2x, yeah, okay. So what have I just learned? I've just learned that the roots of this cubic in the top are in fact, well, -2 is a root, but -2 is like a root again. So -2 is a double root, and also x minus 3. So this becomes x minus x plus 2 squared, x minus 3 over, so there's my cubic in the top. That took some work to get there. And this, of course, is x plus 2, x plus 1. Okay, so now there's an exciting moment because something kind of happened that hasn't, well, it happened only sort of one time on a very, very easy example, which is there's a factor in both the numerator and denominator. Okay, what do we know about this when there's a factor in both the numerator and denominator? Can I just simply cancel an x plus 2 out of the numerator and denominator? The real answer is basically yes. Basically, you kind of can just cancel x plus 2 from the numerator and denominator. And in fact, the simplest, most clear way to do this problem is to cancel it. And to just simplify your life with this simpler rational function. This one over here. Okay, so let me cancel the x plus 2 in the denominator and cancel sort of one of those factors. All right, now as we discussed in a previous class, it's not technically exactly true that this function f equals that. In fact, probably what we should do to preserve, maybe I shouldn't write this kind of canceled like that because it kind of makes it harder to see what's going on. So what was that? X plus 2. Okay, so there we go. Well, what we have really done is we're sort of deciding now to focus on this kind of other function over here. And what is this other function? Well, let's call it g. G is x plus 2, x minus 3 over x plus 1. Okay, and let's take a moment to observe that g and f are basically the same function. What do I mean by basically the same? Well, if this is f, I mean this is f right here, and this is g, then let's compare and contrast f and g. Well, if you give me any number, just pick a happy number like 10 or something like that, then if you plug it into g, you're going to get, whatever you get. And when you plug 10 into f, you're going to get all those same things, plus an extra x plus 2 over x plus 2. But in the case where x is 10, that's just like an extra 12 over 12, that's just 1. And so it really is disappearing for virtually every single possible real number. When you plug it into f, what we get is a number which is in the numerator and denominator, which cancels and therefore has no effect on the overall value of the function. Therefore, f and g really are exactly the same, except for one thing, which is with one number, -2. So I'm even just going to write that down, right? For x not equal to -2, f of x equals g of x. And now for x equals -2, then we need to be careful. What can I say about f of -2? Well, f of -2 does not exist. Because when I try to plug -2 into f, I get 0 over 0. That's just undefined, and so the function sort of doesn't live there. But what is g of -2? Well, I think we should just simply compute it. What is g of -2? Well, it's 0. Okay, so there we have it. The fundamental relationship between f and g is that they are exactly the same value for all real numbers except -2, at which g of 2 is 0 and f of 2 does not exist. Therefore, this is the bold move that I am going to make now because I'm experienced with these kind of problems, and you should make this bold move in the future as well. I shall simply choose to graph g. Because if f and g are the exact same functions except for one point, then I'll just graph g, and by graphing g, I will have graphed f. And this is a good choice because g is just an easier function to graph. So let's put f kind of out of our minds now and just focus on g. Well, what is g? It's this. It's x plus 2, x minus 3 over x plus 1. So let me make a sign chart for g right now. G is going to change sign at -2, -1, and 3, and it's a cubic, so it's cubic-y, I should say. The corresponding polynomial is a cubic with leading coefficient 1, so it's going to be negative, positive, negative, positive. This is me describing the g function. Maybe I even want to find the y-intercept of the g function. So that means that I should multiply out this numerator, which is x squared. Well, I actually already had it before I erased it. It's minus x minus 6 over x plus 1, at which point we see, and I'll even put a box around that maybe because it's a nice thing to know, that the y-intercept is -6. So when you plug in 0, you get -6. And I'm just going to generally do all my analysis on g. And that, for example, what are the roots of g? Well, the roots of g are -2 and 3. Does g have a vertical asymptote? It surely does, at x equals -1. So I have a vertical asymptote, I have the roots, I have the y-intercept, I have the function written like this, I have the function written like that. There's actually a quite easy rational function to graph this g function. There's one thing left to do, which is to do polynomial long division. And when I do polynomial long division, I'm going to do this right now, what happens, x squared minus x minus 6 divided by x plus 1. So this will be, I think, pretty easy. This is going to go in x times, and I get x squared plus x minus 2x minus 6. So that's going to go in minus 2 times, and that gives me minus 2x minus 2, and that gives me -4. Okay, so let's just double check that so we know we didn't make any mistakes. What happens? Yeah, x times x squared plus x minus 1 -2. Boom, 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 boom. That goes to -2 times. Yeah. Okay, grand conclusion is that the g function is just the line x minus 2 plus some just extra stuff. But that extra stuff is just 4 over x plus 1. Okay, by doing it this way, I achieve a kind of a clarity about this g function. What I learned about this g function is that it has a slant asymptote of y equals x minus 2, and also that g doesn't cross y equals x minus 2. And why doesn't g cross? Because there's no x value for which this function equals x minus 2. This numerator here is 4 always. Therefore, you should say to yourself that 4 over x plus 1 is never 0. So since 4 over x plus 1 is never 0, there's always going to be a little bit extra more than x minus 2. Okay, now when I go to graph this, once again, I'm doing this, you know, the right way. Okay, what should I do? Well, I have a vertical asymptote at -1, so let's just throw that in there. I have a slant asymptote of y equals x minus 2, so I'll just throw that in there also. I have some roots. Where are they? Those roots are at -2 and 3, so boom, 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 and boom, 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 boom. I have a y-intercept of -6, and that's pretty much it. And I know I never crossed my slant asymptote. So, using my sign chart as a guide, my function is negative until I get to -2. There's a root at -2. In between -2 and -1, it's positive, so that must mean it goes up here, becoming huge. On the other side of -1, it's also huge, but it's a huge negative. I have this slant, I have this y-intercept of -6. It was -6, right? Yeah. Negative until I get to my root at 3, and positive thereafter. So, that is it. That is the graph of g. Done. But, now that we're all done graphing g, we should return to the fact that we are actually graphing f. And if we're actually graphing f, then we have to respect the fact that f has this one difference, this one fact about it that g doesn't have. And the one fact is that g of -2 is 0, but f of -2 is undefined. But since g and f are otherwise identical, I already have graphed f by virtue of graphing g. And so the only thing I do is I add in this little hole here, I make a giant hole to sort of shout to the world, hey everybody, the point that would normally be located here at the hole location, this point -2, 0, is in fact, you know, not a point of my function. So we say that f has a, you know, f has a hole at -2, 0. Okay, that's the whole function. It's done right now, and that's it, and we're so happy. Okay, what did, however, many of you probably do? What many of you probably did was you didn't do polynomial long division on g. That's kind of a pro move. What you probably did was, if you were lucky, factor correctly, cancel the x plus 2's, write g like this, make your sign chart based on g, hopefully, but then when you went to go, and I need more space, so I guess I will erase, I don't know, everything. What you probably did was you did polynomial long division on f, and then maybe you just got confused or something like that. So let me just make now the mistake that most of you probably did make. You would have to be either very perceptive or very lucky to avoid this mistake. Yikes. So, let's go. X squared goes into x cubed x times. And then we get x cubed plus 3x squared plus 2x. Just like to say that I don't recommend doing this. I think what I did already was more clear. But nevertheless, we push on. So this is minus 2x squared. -8 minus 2, so that's -10x. minus 12, and that's going to go in minus 2 times. So we're getting the sort of same answer or something like that. So then we get negative 2x squared minus 6x minus 4. And when we subtract here, we get negative 10 minus negative, whoa. So we get negative 4x minus 8. Okay, and that's just all true. Okay, and so what might have happened now, and in fact everything I'm writing right now is not wrong, what might have happened now is that you concluded that f was x minus 2 sort of plus negative 4x minus 8 over x squared plus 3x plus 2. And if you were not careful, you would therefore have convinced yourself that at negative 2, this function crossed its asymptote somehow. Okay, in other words, you may have reasoned like this, plus, let's see, I'll just take a 4 out of this numerator, and so therefore it's x plus 2. But of course, this is just x plus 2, x plus 1, and I'm kind of sort of giving it away now, right? Because, yes, a superficial analysis of this factored form of f seems to indicate that when x is negative 2, that this whole thing is 0 because the numerator is 0, and hence the function crosses the asymptote. And so if you had a lot of trouble graphing this function because you couldn't quite figure out how this function was going to cross the line y equals x minus 2 at x equals negative 2, which by the way it doesn't, then maybe you got lost. But now that I have written it like this, of course we see that this x plus 2 is like not really there, right? You can cancel it again, and therefore what that really shows is that f is x minus 2 minus 4 over x plus 1, which, by the way, this was just g. This is exactly what we got when we did g. So I avoided all of this by just doing my polynomial long division with g, as should you. But if you do your polynomial long division with f, as you may have done, the explanation for why the function does not cross there is because when x is negative 2, in fact, the function is not 0. When f is negative 2, the function is undefined. And if you then cancel from the numerator and denominator, then you see that there is no crossing of the asymptote. And I think you should just not do it this way. I think it's just easier and simpler and more straightforward to do your polynomial long division on g, which is the canceled function. Okay, that was pretty hard. That was 4 problems done very thoroughly. You had even 2 more for homework. Man, that's a lot of work. So hopefully you are successful, were successful, and I'll see you next week. Goodbye.